Hello everyone. Today we're going to discuss a question from AQA Physics, and this question is related to momentum and force. So, well, we have a situation. A student is standing on a force-sensitive plate, and she's jumping and then landing, and it is shown by the graph. So the three positions is here on in the graph. The first position, the student is just standing. So when the student is just standing, it is position A, and the y-axis is force, and she's standing on the force meter. That's why we say that when she's standing, the reading shown here, this is 250 and 5 squares. So each small square value is 250 over 5. So that is 25. Not 25. Well, it's 50. Yeah. Okay. So this is 550 then. So it means that the Newton meter is showing 550 when she is standing at A. Now at B, she jumps up. So the reading changes from 550 to somewhere here, which is, you can say 1, 2, and 2.5. So 2.5 means 50 into 2.5 means 125. So you add that. So it means that it is 1625. It changes to that, and then it goes back to 0 again. So at this time, she is going to jump up from this point. Okay, so area under this graph gives you what? It gives you change in momentum, because we know that if it is force time graph, so the area under the graph is F into T, which is change in momentum. So the area under the graph gives you change in momentum. Okay, then the reading at C becomes 0. This means that she is out of touch now, completely out of touch. She's in air. Till this point, she is getting out of touch. And at here, 0.3 second, she's completely out of touch. And then at D, again, she begins to land. So here she's landing. So as she's landing, she's applying the force on the Newton meter, on the force sensitive plate. That's why the reading is increasing. Okay. So first thing is you have to understand the question very carefully. So you have to show that the mass of the student is approximately 56. So that we will take from A. As the force is 550 newtons. So you would say this force is her weight, and weight is mg. So you will say, okay, it is 550 weight, m you have to find, and this is 9.81. So you get this answer. So the prox answer is 56 kg. Okay, let's move to the next thing. You have to show that the student gained approximately 150 kilogram meter per second of momentum when she jumps up. Use the part of the graph labeled B. This is a big hint for you. Big hint, right? Okay, so the gain in momentum, because she was at rest initially, speed was 0. So you know momentum is mv. So m into 0 is 0. That's why her initial momentum is 0. And then she begins to move up. And you have to tell that the momentum that she gained is 150. Okay, and this is a big hint for you. So you will get back to that point to graph. You'll say, okay, let's look into the graph now. Let me zoom in for better like view of it. This is jumping all around. Okay, so now you look over here. Let me zoom in maybe a bit more as far as it remains over there. Yeah, this is a better view now. Okay, so what you will do? Oh, just stand over there. Okay, so now look here. This is the time when, you can say this is the time when she leaves. So 0.10. And then you have to see that when she is getting out of contact, right? Okay. Okay, so well, for this B part, where you have to tell how much is the change in momentum, I told you that this area under the graph gives you change in momentum. So what you do is you go from here, right? Because this is where the reading was constant, and this is the area where reading has changed. Now you have to find this area. So that will tell you the change in momentum. This is irregular shape area, irregular area. So how you can find this area? So there are two things that you have to learn. Number one is counting square method, CMS, counting square method. And number two is drawing regular shape method, DRS method, right? So counting square method and drawing regular shape method. Counting square is that you have to count how many squares are there. So for that, what you do is you generally count these big 5x5 blocks. 1, 2, 3, 4, 5, 6. And then you will see how many are the rest of them. So you count the number of big squares, and then you multiply that with area of the one big square. So that will give you the total area. The other method is drawing the shape. Okay, drawing the shape, how you would draw the shape. So looks this looks like here the area is like, let me just draw a straight line over there, and it's like coming down all the way from here. Or maybe we can change this. It's difficult to draw here with this stylus, but I will try to make one. So I'm going down from here, right there, and then I'm going over there, and till this point, and then I am going down from there to this point. Okay, now you can see that I have added some extra shape. This is extra, and I have not included this one. But this forms a regular rectangle. So this is the width and this is the height. So you measure that, and area is width into height. And then you count the small squares, which you have counted extra. Just count them. And then you can find the change in momentum by total area minus small square area. So you have to count that how many small squares are there, right? And then you will subtract them. Of course, their area, using the same formula, like the area is equal to number of small square into area of one small square, right? So doing that will give you the change in momentum. I hope that serves the purpose. Okay, so what I have calculated, my answer was coming out to be 163, which was the upper range. Okay, calculate the speed of the student as she leaves the plate. Okay, so for this, use your answer to question to 8.2. This is again a big hint. So in 8.2, you have found the change in momentum, which for me was 163 kg meter per second. And the mass of the student was around 58, if I am, oh no, sorry, it is 56. Yeah, so this was 56 kilogram. So now you have to find the change in, you have to find the speed. So change in momentum is, mv minus mu, and as u was at rest, so u is 0. So change in momentum is mv minus m0. So change in momentum is mv. And now you put the value, change in momentum is 163, and mass is this, and you can find that. So divide 56, so you can get around 163 divided by 56. So the speed is around 2.9, which is, I hope, within the range. Okay, the next, calculate the time the student is in air. Use your answer to question 8.3 and a suitable equation of motion. See, again, big hints. Like, this is very easy. They're telling you like how to do it, how to do it. And this is where AQA is taking over Cambridge. They will never tell you, Cambridge will never tell you how to do this. They're telling you that you have to use your answer and you have to use a suitable equation. This is, let's say, my challenge, that this is never given in a Cambridge question, that they will give you such a big hint over there. Okay, so let's solve it. You have to find the time that the student remains in air. Let's say the student was here and this was at A, and when she begins jumping, moving up, let's say this was during phase B, he goes up and then she comes down again and he got in contact. So basically she goes up and then she comes down and hit the plate. So you have to tell that for how long she remains in air. So we say, okay, we have her initial speed 2.91, and we know at highest point speed is 0. When she reaches at the highest point, our velocity becomes 0, and as she's in free fall, so acceleration is minus 9.81. You have to find time, and over here the displacement is not given, so you have to use v is equal to u plus at. So this is 0, and this is 2.91 minus 9.81 into t. So this is like 9.81 t, 2.91, and you divide 9.81 on both sides, and you get an answer of around 0.29, right? So this is the time going up. So as you know, the same time she will take down to come down. So the answer is approximately 0.58 seconds. Okay, determine using the section C of the figure 9, the time the student is in air as recorded by the data logger. This is just reading x-axis when that is 0, right? So you have to just read that time, and that time is almost 0.56 maybe. Yeah, you have to just look from here. So this was the point, and this D is the point. So you have to look right from here to this point. So this is like 0.8, 1, 2, 3, 4, 0.84, and this is 0.29. So you just subtract to 0.84 minus 0.29. So you get answer of 0.55. Yeah, so that is the time, 0.55 seconds. Okay, explain without further calculation, like no calculation, whether your answer to question 8.4 or your answer to question 8.5 has the smaller uncertainty. So this question is related to the uncertainty, right? So you know that when we take some reading measurement that do have some uncertainty or some errors in that. So we can say that in 8.5, there will be the smaller percentage uncertainty because, the estimating the area under the curve is likely to be inaccurate, right? Because there are more error in the calculation of the area under the graph, as you're just assuming that. So you can say, well, 8.4 or 8.5 has the smaller uncertainty. So yeah, look, in 8.4 is this, calculate the time the student is in air Um, and then he was in air for 0.58, and then in 8.5 is the student is in air. Well, it's the same thing, but both are different method. One, you are just reading from the graph, and this one you are calculating from 8.3 as well, and from using the suitable quantity as well. And one time is 0.58 and the other time is 0.55. So, well, the percentage uncertainty depends on which thing. So first of all, both are the times, but one time you just directly read from the axis, and for the other time you have gone through some calculation from here, and over here you were doing the approximation. But in this area, in this time that you have calculated from here, it's just you just have counted the number of squares. So there is less error over here because you have just directly reading it. And over here there are more error involved. So it means that you will be saying that there will be less error when you directly measure your answer. So we say that uh, 8.5 is having less percentage uncertainty since you are directly counting from scale without estimation. In 8.4, you have made big estimation over there. Okay, next the student step off the platform from onto the force sensitive plate. Okay, from a platform on that. The student steps off the platform twice. The first time she lands, she keeps her legs straight. The second time that she lands, she bends her knees, increasing the time to decelerate. Explain how increasing the time taken to decelerate affects the force on the plate. Refer to one of your Newton's laws of motion. Well, you know that Newton's second law of motion is about resultant force acting on object is equivalent to rate of change of momentum. So you know that as she bent her knees and takes more time to land to stop. So F is delta P by T. So as T increases, the force reading is going to decrease, right? So this is the answer. So you will say from Newton's second law, force is equal to change in momentum over time. And in both scenarios, our change in momentum will be same. So you say that as this is constant, so force is inversely proportional to t. So in the second situation, she's taking more time, so less force will be there, right? And we say that as she's taking more time, so there will be less change in reading on the sensitive platform.